Once we've analysed a set of data, perhaps using averages, perhaps using some other data analysis methods, it can be helpful to have a way of presenting the data, different ways that we can set it out, rather than as just a list or a table of numbers, something that's a bit easier to understand, or perhaps easier to look at, perhaps easier to further analyse. So we turn to these methods of data handling. Pete is collecting information on the colour of people's cars. He asks people what colour car they drive and records the information in a table. And then the question says, using the information in the table, complete the pictogram. Well, then the first question obviously becomes, what is a pictogram? Now, a pictogram is a way of taking numerical information and displaying it visually in a very easy to understand way. A pictogram takes a particular picture. It could be anything. A particular visual symbol. It could be a square, a circle, they're kind of common ones. But you might get more context-specific ones like a smiley face or a pizza or something like that. The idea is that this visual symbol represents a particular quantity given by a certain key, like in this particular one here. In this key, these four little boxes joined together represent four, in this case, cars. Every time we have that symbol, we are giving 4. To match up the information in the table, so in the table we have the different colours and we have the different frequencies. Frequency, remember, is how many times something happens. Matching up the colours in the table and the pictogram, we can see how this key works. Red car. Red cars. 4 red cars, so we just have one of those boxes there. The green. Just 2 cars, so we only need half as much. Now we should be able to transfer information between the table and the pictogram using that key. If we look at the blue cars, for example, we've got 1, 2, 3 copies of that box. So there's 4 cars there, 4 cars there, 4 cars there, and then a quarter of the box. Well, if the whole box is 4, then a quarter of the box must be 1. So we've got 4, 8, 12, 13 cars. And if we wanted to try and fill in the rows for white and silver, in the table we've got 20 white cars. So we're going to need 4, and then 8, 12, 16, 20. And for silver, 10 cars, so we're going to need 4, 8, 10. Again, a reminder with these pictograms, the visual symbol could be anything but needs to be defined by the key. All pictograms must have a key so that it is obvious what the visual symbol is representing. Is it representing 1? Is it representing 2, 4, 10, 100? We need to know. We need to have a key to tell us that. Question 2, we've already talked about that. How many people drive blue cars? Complete the table, and it was 13. Another way we can present data is to construct something called a stem and leaf diagram. Now, it is easiest to explain what a stem and leaf diagram is by just building one and then explaining where the name comes from. So with a stem and leaf diagram, we would have something like this. We would have a set of data. A maths test is marked out of 50. The marks of the class are shown below. Now, if we look closer at that list, we can see that some of the numbers are less than 10. So we've got 7 there, and 3, and 8, and 6. We've got some numbers in the 10s, some in the 20s, some in the 30s, some in the 40s, and then one that is 50 just there. Here's what we do. We set up, first of all, a stem. Now, this line here is our stem. And along the stem, we write down the starts of those numbers. So we have some that are in so we have some numbers that are just units. They have no tens because they're less than 10, so that's the 7, the 3 and so on. They have no tens. There are some numbers that are tens numbers like 17 and 19. They have one 10. Some numbers in the 20s, so they have two tens. Some in the 30s, so they have three tens. Some in the 40s, so they have four tens. And then that one 50 there. So what we've done along the stem is we've written down the tens numbers. No tens, one ten, two tens, three tens, four tens, and five tens. That is our stem part of the diagram. We now need to construct the leaves. And the idea is that each of these numbers is going to become a leaf in some way. They're going to go here. So we've ruled off underneath each 10 to split off into different rows. And we're going to fill these numbers in along the correct part of the stem. We're going to do this one set at a time. So the first thing we're going to do is we're going to look at these units numbers, these numbers that are less than 10, these that have no tens. And what I'm going to do is I'm going to pick them out of here and I'm going to just jot them down to the side. I'm going to do this carefully, I'm going to do this in order. So I'm just going to pick them out in the order that I find them in the list. So here we have the 7, and we have the 3, and we have the 8, and we have the 6. And as I pick them out, I'm going to cross them out of the list so that I'm not looking at them anymore. The 8 and the 6. I'm going to check carefully to make sure that there aren't any I've missed. No, there aren't. Okay. 7, 3, 8 and 6. What I'm going to do is I'm going to fill them in along here. But I'm going to put them in order, smallest to largest. I'm going to go for the 3 first, and then I'm going to go for the 6, and then the 7, and then the 8. And I'm going to spread them out a little bit just to keep it nice and organised. So here we have the 3, the 6, the 7 and the 8 with no tens associated. So what I'm going to do now is I'm going to go through and I'm going to pick out all of the tens numbers. I'm going to do it carefully again. I'm going to jot them down as I find them. So we've got a 17. We've got a 13. Cross both of those off. We've got a 19. And we've got a 10 and a 14. And we've got another 17. I am going to write it down twice. There are 2 in the list of data. And then there's an 18. And a 12. And another 17. So there are in fact 3 of those, but I am going to write all 3 of them down. I'm then going to take each of these numbers and I'm going to write them in my stem and leaf in order of size from smallest to largest, but I'm going to write them in a very particular way. So the smallest number we have in here is the 10. I'm going to put the 10 in. We've already got the 1 though. The 1 is here on the stem. So what I'm going to do is I'm going to put the second bit that makes it a 10. So I'm going to have the 1 and the 0 to make 10. Next one will be the 12, so the 1 and the 2 to make 12. And then the 13, so the 1 and the 3 to make 13. And then the 1 and the 4 to make 14. And then the 7 and the 7 to give me the 17s. And then an 8 and a 9 to give me the 18 and the 19. So I've written all the tens numbers in my stem and leaf diagram. 1 and 0 to make 10, 1 and 2 for 12, 1 and 3 for 13, 1 and 4 for 14, 17, 17, 17, 18 and 19. So the next thing I'm going to do, I'm going to go through and I'm going to fill in the 20 numbers. And I'm going to fill them in the same way. So for the 20s, we've got a 27, and a 21, and a 24, and a 24 again. And then we've got a 25, a 23, and that's it. I need to put those into my stem and leaf diagram. So on the stem we've already got the 2. We just need to make the leaves now for the units numbers. So 2 and 1 for 21, 2 and 3 for 23, 2 and 4, and another one, 2 and a 5, and a 2 and a 7. And we've filled in my 20 numbers. I'm then going to do the same for the 30s, I'm going to do the same for the 40s, and I'm going to do the same for the 50s. And by the time we're finished, we should have a stem and leaf diagram that looks something like this. A couple of things we should do. A couple of things we have to do, in fact, before we finish it off. Good thing to do would be to check that we have got all of the information from the list in the stem and leaf diagram. Nice, easy way to check that. Count up how many things are in the stem and leaf diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. How many pieces of information are in the original list? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 rows of 10 is 30. All of the information has been transferred into our stem and leaf diagram. The next thing we need a key. There's a big clue that we need a key because there is the word key written there, but we also actually need a key to tell us what this stem and leaf diagram is showing us. We know that here we have the stem, and the stem is the tens. So that this number, for example, is 4 tens and 5 units, 45. So that this number here, for example, is 2 tens and 4 units, 24. But without that context, we only know that because we built the stem and leaf diagram. Without that context, is this here 12? Or is it 1.2? Or is it 102? We don't know. So we need some way of showing it. So what we're going to do is we're going to pick something from the table. It can be anything, doesn't matter which. I'm going to pick this one here. I'm going to do 1, and then a line, and then 0. And I'm going to say that that is equal to 10. I'm going to pick one of these examples of stem number and leaf number, write them down with a little stem in the middle, and then say what that is equal to. So this is a stem and leaf diagram, an ordered stem and leaf diagram, in fact, because they are in order. It is possible to construct an unordered stem and leaf diagram. We just tend not to bother. It's more useful to construct an ordered one. Why? What have we done to the data in putting it in an ordered stem and leaf diagram? Well, we've put the whole list in size order. We've got 3, and then 6, and then 7, and then 8, and then 10, and then 12, and 13, and 14, and 17, and 17, and 17, and 18, and 19, and so on, up to 50. There might be lots of reasons why we want to put a set of data in size order. But now we've put them in size order, there is one useful thing, one useful piece of data analysis that we can do on it. We can now find the median. Because for the median, remember, the median is the middle value, but we have to put them in order of size first. Well, we've just done that. We've just arranged the numbers into order of size. And what we can do is we can go through and we can work in towards the middle, crossing one off from the beginning and one off from the end, until we're left with that middle value, or 2 that our middle value has to be in between. Now, when we're doing this crossing off, we have to be very careful that we stick with the order that we're going and that we actually work in from both ends of the list. It's only really important at the jumps between the different bits of the stem, the different layers, but here we go. So we can cross off the 3 and the 50, we can cross off the 6 and the 49, be careful that we're working down the list, 50 then 49, we can get rid of the 7 and the 46, and we can keep working in that way, crossing off 1 from each end of the list in pairs until we are left with, in this case, 2 that our median must be between. Must be exactly halfway between there, and so the median would be 23.5. Now, pictograms and stem and leaf diagrams are particularly good for making quick visual references to the general trend of a certain set of data. We can see where the majority of the data is clustered. And they're very easy because they're both very visual, particularly the pictogram, which is based around visual symbols. Sometimes, though, we might not want to make judgments on one particular set of data. We might want to make judgments on two. In particular, we might want to investigate whether or not there is a link between two distinct sets of data, two different sets of data. The first thing we need, a piece of terminology. The link between two sets of data is called the correlation. So if we're investigating whether there is a link, we are investigating the correlation. And we'll talk about the different types of correlation, the different types of link that we might have between two sets of data as we go. But it makes sense that sometimes we might have two different things that we've measured or researched or collected data on, and they might be linked. For example, I want to investigate whether there is a link between height and shoe size. Just on gut feeling, it seems fairly plausible that there is probably some link between height and shoe size. We might even take a bit of a stab at what that link could be. It would seem sensible to us to suggest that perhaps the taller somebody is, generally speaking, the larger their shoe size would be. But it's not enough to just guess that. It might be okay to think that, but we then want to investigate whether it is true or not. We might want to prove whether that's true or not. So we might collect some data. I ask 15 people to tell me their height and their shoe size, and I list the results in the table below. So we've got people A through O, that's 15 different people, and then we've got their shoe size listed, and then their height listed. So person A, for example, has a shoe size of 7 and is 1.63 metres tall. Person B has a shoe size of 8 and is 1.68 metres tall, and so on. So we've collected shoe size and height for each of those 15 different people. And what we're going to do to show whether there is a link, whether there is a correlation between those two different data sets, we are going to draw a scatter graph. And a scatter graph is the easiest way to investigate correlation, to investigate this link. So what we're going to do with a scatter graph is we're going to start off with a set of axes. We've got a horizontal axis and we've got a vertical axis. On the horizontal axis, this is the one at the bottom, we are going to fill in one of the data sets along that axis, and we're going to fill in the shoe size down there. So we have got, looking along this list, we've got shoe size 7, 8, 9, 10 and 11 represented. So we've got 7, 8, 9, 10 and 11 represented. I'm going to also write down what that is, and that's shoe size. We need to make sure we are labelling the axes so that everything is nice and clear and readable. What is this weird squiggly line for? Well, our scale does not start at 0. So what we're doing is we're just having that little squiggly line to show that there are numbers between, like 0 is here, but we are starting our numerical scale at 7 because we're not interested in anything between 0 and 7. 7 is where our data starts, but there, where the two axes meet, is the 0 point. We also need to have our information up the side, so we can look at the different heights. We're going to put our height up the side, so I could label that if I like. Height in meters. We want to label everything, we want to keep it nice and clear. The idea with any of these graphs and charts is that somebody who does not know how it's being constructed could look at it and understand exactly what is being shown. That's the point of these data handling, data presentation ideas. They need to be easy to understand by people who don't know how they've been made. So up here we're going to have our height. Now again, we've got the 0 there where the axes meet, and then we've got this little zigzaggy line to show that we're missing some stuff out. The smallest height that we've got recorded in this table is the 1.63 metres, and the tallest height is 1.85. So we only really need to have our scale between those two numbers. What I'm going to do is I'm going to go up in jumps of 2, and I'm going to start at 1.60. I'm going to use a pencil for this. As with most of these drawing things, it's a good idea to use a pencil so that you can make changes as we go. But I'm going to go up in 2s, so 1.62, 1.64, 1.66, 1.68, 1.70, 1.72, 1.74, 1.76, 1.78, 1.80, 1.82, 1.84 and 1.86 there at the top. The idea is I'm now going to take each person one at a time. So I'm going to do person A and I'm going to mark them somewhere on this diagram. I'm going to take person B then, mark them somewhere on the diagram, and so on all the way through to person O. Here's what I'm going to do. I'm going to look at person A. I'm going to notice that they have a shoe size of 7, so I'm going to be going up from shoe size 7. And they have a height of 1.63, so what I'm going to do is I'm going to go up from shoe size 7 to a height of 1.63. Well, there's 1.62, there's 1.64, so 1.63 will be in the middle. And I'm going to put a cross. I'm not going to label that with anything. I'm not going to write person A on it, because I'm just collecting all the data on one. I don't need to know which bit of data belongs to which person. I just need them all marked on the diagram. I'm going to end up with 15 crosses on here. We're going to mark person B. So person B has shoe size 8 and then 1.68. Person C, 9 and 1.75. Person D, 10 and 1.78. 1.78. Person E, 11 and 1.85. Person F, 7 again, and 1.68 this time. So I'm going to mark that one on there. And I'm going to keep going until all 15 people are marked on my diagram. Until we end up with something that looks a little bit like this. So 15 crosses marked on that diagram. And we can see from looking at the crosses that it seems to be the case that, generally speaking, apart from a couple of perhaps slight outliers, but generally speaking, the bigger the shoe size, the taller the person. There's this sort of upward trend, upward slope of the data. We can make that trend even more clear by drawing what's called a line of best fit. Now, a line of best fit is a single line, a straight line, usually, that we draw on a scatter graph. We cannot join up the points here. It's not the kind of graph where we can join them all up. Because what order will we join them up in? Do we go up and then down and then sort of zigzag around? It's not obvious what order we would join them up in. And it wouldn't be practical to join them up in order from A through O. But what we can do is we can draw this idea of a line of best fit. Now, a line of best fit is a single line, usually a straight line. It could be a curve if that's what the trend seems to be showing, but we're only ever going to come across straight lines, that goes through or near as many of the data points as possible. Now, it's called a line of best fit for a reason, and it's just that, a best fit. There are several different acceptable lines of best fit that you could draw, and one person might draw a line of best fit that's slightly different to another, but that's okay. There's usually a selection of sensible lines of best fit that you could draw, but the idea is to try and draw a straight line through or near as many of the points as possible, trying to keep roughly equal numbers above and below the line. So what I'm going to do is that you play around with your ruler a little bit on this one until you get something that's got roughly equal numbers above and below. I'm going to go for that one, I think, and I'm going to draw that in as a nice straight line. And there is my line of best fits. That most of the data seems to be heading along that kind of trend. We've got a couple below and a couple above. We've got this kind of thing, 2 here and 2 here, and it almost goes through this point here. A line of best fit, then. Single, usually a straight line that goes through or near as many of the data points as possible. Now, why is a line of best fit particularly useful? Well, 2 reasons. First is that it helps us to see more clearly the link, the general trend in the data. There's an upward slope to this line of best fit, which suggests that there is a general upward trend in the data, in the sense that as shoe size increases, height generally seems to be increasing as well. And if we were asked to describe the general trend, that would be our description. As shoe size increases, height increases as well. There are obviously some outliers though. This piece of data here, for example, seems to be a bit of an outlier, a bit of an exception. It seems to defy the general trend slightly, and that's okay, that's normal. Most sets of data will have, particularly real life ones, will have some outliers, and if we needed to go into a discussion of that, this data point being so far away from the line of best fit is easy to identify as an outlier. So the first thing that the line of best fit does is it shows us the general trend more clearly, and it lets us identify outliers, things that buck the trend. The second thing a line of best fit is useful for is it's useful for estimating. If we were asked to estimate pieces of linked data, then we could. We might, for example, be asked to estimate the shoe size of somebody who is a particular height. Well, we could do exactly what we did with graphs and using the line on graphs to do that. If we were estimating the shoe size of somebody of height 1.73, for example, we could go across to the line of best fit from the 1.73, and then we could head down to the shoe size axis, and we would be suggesting a shoe size of between 8 and 9, perhaps 8.5 there. Now, there is something very important with correlation to bear in mind. The classic phrase that gets trotted out is that correlation is not causation. Now, what we mean by that is that if we draw a scatter graph, if we investigate the link between two types of data, this correlation, and we find that there is one, the presence of a link, the presence of a type of correlation, does not necessarily mean that one piece of data causes the other piece of data to happen. It could be that the link is one of the pieces of data causing the other one to happen. It could be that there is a causation, but it could be that a change in one piece of data and a change in the other piece of data, it could be that they're both influenced by something else. It could be that they're both caused by a third party. Or it could be that the link is just coincidental. Okay, so there are three types of correlation that we need to be aware of. Three types of links between data. The first is one we've already seen, where the data will look a little bit like this. A general upward trend in the data. As one increases, the other increases as well. And that is a positive correlation. A general upward trend. As one piece of data increases, the other one also increases. We could have the opposite of that. A general downward trend. As one piece of data here increases, the other one decreases in size. So as we move along the bottom and get bigger, we get smaller up the side. And that is a negative correlation. There are different types of positive and negative correlation we could have. If it's a very steep line, we could have a very strong positive link, or we could have a much weaker positive link. Same with negative. We could have a very strong negative link, a very clear-cut positive or negative correlation, or we might have one that's just a general upward or downward trend, a fairly weak link, but a link nonetheless. Example of a positive correlation, something like, say, rainfall and the number of umbrellas that are sold. The greater the amount of rainfall, the greater the number of umbrellas that are sold. Example of a negative correlation, something like the amount of pesticide used in a garden and the number of garden pests. You increase the amount of pesticide, you decrease the number of garden pests. The third relationship, the third link, well, actually it's a bit of a cheat. It's something that would look a little bit like this. Very scattered, crosses all over the place. No particularly obvious positive trend, no particularly obvious negative trend. In fact, this is for data where there isn't a link at all. This scatter graph is showing us no correlation. An example of data, two different data sets that have no particular link between them. The size of television and the average time spent watching television. It's probably the case most of the time that they would not show a particularly strong link either way. The two pieces of data would be fairly unconnected. A bar chart easily compares frequencies by representing that frequency as the height of a rectangular bar. For example, the bar chart shows information on the different sports that people play. First thing to notice, we have a nice clear title at the top. Number of people who play different sports. As with any of the charts, remember, a title and some labels, very important so that we know what the chart is showing us. We then have across the bottom the types of sport: football, tennis, basketball, cricket, rugby, athletics and hockey, and up the side we have the number of people. Notice that we could label that as frequency instead, and in fact the table underneath, which lists the same sports, has labelled it as frequency. We then have numbers up the side, so 0, 2, 4, 6, 8, 10, 12, 14, and presumably 1, 3, 5, 7 and so on in between. The height of the bar then, in each case, because we have these rectangular bars, the height of the bar in each case represents the frequency. So for question 1, complete the table to show the frequencies. Football, that bar reaches up to a height of 6, so we can fill in 6 as the frequency. Tennis, 2. Basketball, now there doesn't appear to be a bar. It is in the table, however, so it's not just that it's been missed off. It is in fact that the frequency is 0. Cricket up at 10, rugby up at 8, and then athletics up at 12 there. And what we've done is we've transferred the information from the bar chart into the table. We could go the other way around, because the next question says 11 people play hockey, and we're asked to draw the bar to represent this. So what we need to do is we need to draw a bar above where the hockey is on our bar chart, up to a height of 11. Well, 11 will be somewhere between 10 and 12, so it will be up to about this height here. We want to try and make the bar about the same width as the other ones. Bars in a bar chart are always the same width. We can do this by eye, it doesn't need to be amazing, but it should be about the same width as the other ones where possible. And there we go, hockey. We could even shade that in if we like, just to make it a bit more clear. Another bar chart now, showing us at this time the heights of adult males in inches. We know it's the height of adult males because it says height of adult males at the top. We then have inches marked along the bottom, 66 through 74, and we have frequencies up the side. Question 1 says, how many more people were 69 inches tall than 66 inches? Well, we could do that. We could first of all look how many people are 69 inches tall. That's 6. And how many people were 66 inches tall? That's 1. How many more people were 69 than 66? Well, 5. Now we've very much skirted round this, but hopefully you've noticed something different about the bars this time. But in fact, question 2 asks us exactly that. What is different about the bars this time? Well, what's different about the bars this time is that they are touching. In the previous example, there were gaps between them, whereas here they are touching. In fact, that is a difference that matters. And the reason that they are touching here is that the 66, 67, 68 up to 74 are continuous pieces of information. They are one continuous set of data. 66 to 67 to 68 to 69. It's not necessarily that they are numerical, it is that they are continuous. Whereas in the previous example, each of the different sports was one distinct thing. So when we're drawing bar charts, if we have continuous data, like this kind of numerical idea, or possibly something like days or months, we shouldn't really be having gaps. We should be drawing the bars touching, drawing the bars directly next to each other, whereas if we've got separate, distinct pieces of data, we should have gaps. As before though, the bars are all of equal width, and the height is showing us the frequency. So what's different this time? No gaps, and continuous data. Draw a frequency graph for the information below to show the number of takeaways people eat in a week. Easiest way to explain what a frequency graph is to just talk through drawing one. A frequency graph is a little bit like a scatter graph and a little bit like a bar chart. It's sort of like a middle ground between the two. Here's how it works. So along the bottom we have the numbers. This is the number of takeaways. So we could have 1 or 2 or 3 or 4 or 5, with the 0 being here in the corner. And then up the side we have the frequency. And we're going to mark both of those. Notice we still need our labels for the axes. Up the side we are going to go 0 in the corner there, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can then mark on the different points. So 1 takeaway, well, that's frequency of 10. 2 takeaways, that's a frequency of 4. 3 takeaways, that's a frequency of 1. 4 takeaways, that's a frequency of 2. And 5 takeaways, that's a frequency of 0. Notice what I've done this time is for each of those sets of data, for each of those pieces of information, I have put a cross. That's where the scatter graph-like bit comes in. However, unlike a scatter graph, we are marking a particular piece of information against the frequency, and that's where the bar chart bit comes in. The height of the cross, how far up the frequency scale the cross is, gives us the frequency, much like the height of the bar on a bar chart. Final thing we need to do with a frequency graph, not a scatter graph. With a scatter graph, remember, we're drawing the line of best fit. This isn't a scatter graph, this is a frequency graph. What we're going to do is we are simply going to join them up in order with a ruler. A straight line for a frequency graph. To draw them up, join up the points 1 to 2 to 3 to 4 to 5. Draw a frequency polygon to represent the following information about the number of hours people work per week. Now we've just drawn a frequency graph. So what on earth is a frequency polygon? Well, actually, they're pretty much the same thing. They're just different names for the same type of chart. What's different here, though, is that we don't have individual distinct pieces of data. We have grouped data. We've got hours of work 0 to 5, 5 to 10, 10 to 15, and so on. It doesn't change much about the way we draw the frequency polygon or frequency graph. It does a little bit, though. Well, the first thing we can do is we can fill in our scales and labels. So along the bottom, 0 in the corner, and then 5, 10, 15, 20, 25, and 30 for the different hours of work involved in the groups. Up the side, we can have 0, and then we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, so it fits. We need to label those, so up the side we have frequency, along the bottom we have hours. We need to draw the crosses on now to show the frequency, so we're going to go to the right height to show the frequency, but where do we draw the cross to show that the data is grouped rather than being individual distinct pieces of data? What we do is we mark the cross in the middle of the group. So for the group 0 to 5, we're going to mark it halfway in that group, so around about here, but at the correct frequency, so a frequency of 1 there. For 5 to 10, we're going to go in the middle of this group, so here, but up at a height of 3. This one here, 10 to 15, so we're going to go in the middle, and a height of 16. Height of 9 for the next one, marked halfway between 15 and 20. Height of 15 for between 20 and 25. That'll be there, and a height of 20 for that final group, 25 to 30. Finishing off the frequency polygon or the frequency graph, nice and simple, just join the points in order with a straight line. Like so. So frequency graphs or frequency polygons, a bit like a bar chart, but without the bar. A pie chart is a visual way of representing distinct groups of data as part of a circle. Now the idea is that the whole circle represents the whole of the data, the total frequency of everything. All the people asked, for example. We then cut the circle up into chunks. And the chunks are done so that the proportion of the circle that's being drawn represents the proportion of the data that is in that group. as in half the circle represents half the data, a quarter of the circle represents a quarter of the data, a tenth of the circle represents a tenth of the data, and so on. Now we can work out what proportion of the circle we need to draw, if we're drawing a pie chart, by working out what proportion of the whole frequency each category is. Or the other way round, we can work out how much of the data a chunk represents by working out how much of the circle it is. We'll start simple. A pie chart is constructed to show the way in which 40 people travel to college. And here is the pie chart. Now question 1 says, if the sector of the circle representing car is 90 degrees, how many people travel to college by car? Well, first of all, we need to know a key fact about circles. And we've had a clue given to us there, and the clue is that 90 degrees. There is something that we know about the angles in a circle. We know that the angles in a circle, or in a full turn, come to 360 degrees. And that is our key fact for pie charts. Everything hinges on that. Because the idea is we're then finding chunks of the 360 degrees. The bigger the chunk, the bigger the proportion of the data. So if the sector of the circle representing car is 90 degrees, how much of the circle is that first of all, and then how much of the data? Well, 90 degrees is a quarter of the circle, so it must be a quarter of the data. The whole circle is 40 people. So we must have then that 90 degrees is 10 people. Because we've divided by 4. Question 2. If the sector of the circle representing cycling is 45 degrees, how many people cycle to college? Well, if 90 degrees was 10 people and 45 degrees, that's half of the 90, must be half of the 10, so there must be 5 people. And we're breaking it down in this kind of way. So 5 people. Question 3 finally. What size of angle represents one person? Well, if we know that 5 people is 45 degrees, or in fact that 10 people is 90 degrees, or in fact that 40 people is 360 degrees, we can easily divide down to get one person. Either by dividing this row by 5, or this row by 10, or this row by 40, we can get down to one person being 9 degrees. Why is that useful? Well, because we can then use that key fact to work out the size, or in fact the number of people, depending on which way around we're looking at the question, of any chunk or group that we like. If we know that one person needs to be 9 degrees, then 2 people has to be 18 degrees, and 3 people has to be 27 degrees, and so on. And that lets us draw pie charts. So let's draw a pie chart. Draw an accurate pie chart to represent the following information on people's eating habits. So we've got 4 different eating habits listed: vegetarian, pescatarian, vegan, and meat eating. We then have frequencies for each of those: 22, 24, 16, and 28. And then we've got a circle drawn underneath with a line in it. To draw a pie chart, we need to know what chunk of the circle each of these groups needs to represent. Well, first thing we need to know is how many people the whole circle represents. So we need to do 22 plus 24 plus 16 plus 28. We need to add those up. So we grab our calculators and we add them up. And we find that they add to 90. So 90 people were asked in total. Now off to the side, I'm going to jot that down as a fact. I'm going to say that 360 degrees is 90 people. Because that's true. And what we need to do is we need to break down to one person. We need to know how many degrees there are for one person. Now we've got options with this. We can either break it down in chunks, a bit like we did in the previous one. We could half both sides and get 180 degrees for 45 people and break it down that way. Or we could just go straight from 90 people down to one person. To do that, we would be dividing by 90. 90 people divided by 90 will take us down to 1. And if we do the same on the other side, we do 360 divided by the 90 to give us 4 degrees for each one person. And that fact right there, that one person is represented by 4 degrees, is our key to working out the rest of the angles. Because if one person is 4 degrees, then 22 people will be 22 lots of 4 degrees, will be 88 degrees. 24 people will be 24 lots of 4 degrees. And will be 96 degrees. 16 people, 64 degrees, 16 lots of 4. And then 28 lots of 4, 112 degrees. At this point, it will be a useful thing to just check that they add up to 360. 88 plus 96 plus 64 plus 112. Do they add up to 360 degrees? Yes, they do. Now, because we're drawing angles, we're going to need one of these. We're going to need to grab our protractor. This line here is our start point. What I'm going to suggest we do is we turn the page. We know what angles we're drawing. We're drawing an 88, then a 96, then a 64, and then a 112. We're going to turn the page so that we're always working in the same direction. I'm going to turn the page to here. And I'm going to start with my line like this. Because then we're just looking at the protractor the normal way up. So I'm going to line my protractor up so that the centre of the protractor is at the centre of the circle, the end of this line. The first angle we're drawing is the 88. So remember, with the protractor, we're using whichever scale starts with the 0. So I need to line it up so that the line along here fits on that line on the protractor, which again, remember, we are keeping pointing towards the left. We must be on the outside one because that's the one that starts at the 0. And I'm going to do this carefully. I'm going to go round and I'm going to mark the 88 on there. And then I'm going to draw that line in. I'm going to go from the centre of the circle through the 88 degrees to the outside. And that's our first group, so that's vegetarian. I'm then going to turn my page again. And I'm going to keep that line on the left, so that we're always keeping the protractor the same way round. The next one I'm going to draw is 96 degrees. So I'm going to line my protractor up so that that new line we've just drawn is our start point. But we're keeping it on the left again, so we're always looking at the same type, the same bit of the protractor. We're on the outside scale again, and we're going to go round till we get to 96. So the 96 is there. And I'm going to draw that line in. There we go. I'm going to turn the page again so that that line is on the left, and while I'm at it, I'm going to label that second section as pescatarian. Third section, we need to draw 64 degrees, starting from that line that we've just drawn. So we're going to start with the 0 again. I'm going to line the protractor up, cross in the centre. We're going to go round to the 64 degrees this time. There we go. I'm going to draw that line in. I'm going to label that section as vegan. Now, the final section has been drawn for us. It should be 112 degrees in size. So I'm going to turn my page one final time until that's on the left. And I'm going to measure that and check that it is 112 degrees, as expected. So we line our protractor up so the cross goes in the centre, and the line of the protractor fits on the line that we've drawn. Measure it round and it comes to 113 degrees, while allowing for slight variations in terms of drawing. We're allowed to be a degree or two out. That seems okay. We can label that section as meat, and there is our finished pie chart. Turn the page back around where it started, and the pie chart is done. Each of the 4 groups are on there, labelled, notice, because we always need to label our diagrams, make them clear what they are showing. And each group, each chunk of the circle is proportional to the amount of the data that is there. Final thing with pie charts can actually be quite tricky to read if we are not very, very careful about what information they are showing us and what information they're not. The pie charts show some information about the numbers of medals won by Germany and by the Russian Federation in the 2010 Winter Olympics. We've got two pie charts, medals won by Germany and medals won by the Russian Federation. This is an actual past paper question, by the way. The first part of the question then, Germany won 7 bronze medals. And then it asks how many gold medals Germany won. So we only need to look at the Germany pie chart first of all. From the pie chart, we know that 7 bronze medals is represented by the 84-degree section there. So then 84 degrees is 7 medals. Now everything within that pie chart will be in proportion to everything else within that pie chart. So if 7 medals is 84 degrees, then we need to work out how many medals 120 degrees is for the gold medals. Maybe it will be helpful then to work out what 1 medal is. Now if 7 medals is 84 degrees, we could divide by 7 to get down to 1 medal. 84 degrees divided by 7 will be 12 degrees. So if 12 degrees is 1 medal, then 120 degrees, how many 12s do we need for 120? Well, 10. So there must be 10 gold medals. I'm going to write that in that section there. Because question 2 says, Katie says, the pie charts show that Germany won more gold medals than the Russian Federation. Is Katie right? And then you must explain your answer. Well, first of all, gut feeling, to yourself. Is Katie right? Yes or no? Those of you that said yes, I suspect, first of all, you said 120 degrees for Germany, 72 degrees for Russia. Germany won more. It's a bigger chunk of the circle. Perfectly reasonable thing to say. But not necessarily true. We only have information about Germany's medals. We've worked out how many gold medals they won. We know how many bronze medals they won. We could probably work out how many silver medals there are, and we could get the total number of medals that Germany won. But we don't know how many medals Russia won. Why is it important to know that? Okay, 72 degrees. Turns out that that is 1/5 of the circle. In the same way that 120 degrees is 1/3 of the circle. So again, just on the actual fractions, bigger chunk of the circle for Germany. So why is that not guaranteed to be more medals? Because it depends on the overall amount. If 1/3 of the circle here is 10, then how many medals did Germany win in total? Guaranteed. Well, it won 30 medals in total, because 1/3 of that would have to be 10. We know that Germany won 30 medals then. We don't know how many medals Russia won. But we do know that 1/5 of their medals were gold ones. Imagine, for example, that Russia won 100 gold medals. It might have done. We don't know. We don't know that they did. We don't know that they didn't. But imagine that Russia won 100 gold medals. 1/5 of Russia's medals then are gold. So how many of Russia's medals are gold? Well, 1/5 of 100 is 20. Did they win 100 medals? We don't know. We've absolutely no idea. But the point is that in this case, if Russia won 100 medals, then Russia won more gold, not Germany. The point is that the proportions for a pie chart only work within that pie chart. Pie charts cannot be compared in terms of comparing the sizes unless you know that the overall totals are the same. The point is then, is Katie right? Well, actually, we don't know. And it is okay to say that sometimes. We don't know. Because it depends how many medals Russia won overall. And unless we know that, we cannot work out the number of gold medals they won, and we cannot compare the two pieces of information.